Good afternoon, everybody. Thanks for this opportunity to speak. And okay, this presentation seems like a bit off topic, especially from the point of view of the hardware software. You will see it's quite different from what you heard till now. But essentially, it's worth speaking about retroreflectors as retroreflectors because they have several applications for studying gravity in slow motion regime and weak regime, and can be also used in the future, who knows, also for gravitational wave detection. So my name is Muccino. I'm from INFN, so National Institute of Nuclear Physics of Italy, particularly from Frascati. I speak on behalf of a large collaboration and also on behalf of point of contacts from ESA. Yesterday you have heard about a very nice comprehensive summary from Luigi Cacciacuoti. And I speak also on behalf of point of contacts for NASA CLIPS missions and ASI representative point of contacts in the context of the INFN Frascati and ASI Matera joint lab. So let's go into the overview, the outline of this talk. Essentially, I'm talking about retroreflectors, in particular, next generation laser retroreflectors. I could try louder. Yeah, so I did this in this way, maybe it's more effective. Okay, now it's better? Okay, sorry for the inconvenience. I have also not so loud voice because of some problems. Okay, so briefly, the outline is the following. I try to speed up a little bit. I will speak about next generation lunar retroreflectors. And in particular, I will speak about their employment in the estimates, measurements of weak field and slow motion regime in South Earth Moon system, especially related to the estimates of weak and strong equivalence principle, and also the estimate of post-Newtonian parameter beta and estimate of the variation of gravitational constant, inverse square law, and within GR and beyond. And in particular, talk about MoonLIGHT, which is the next generation retroreflector for the moon, which was designed in INFN. And there is also another one that is designed in the University of Maryland of the USA. So the INFN one is called MoonLIGHT, which is an acronym, very long but very effective one for moon laser instrumentation for general relativity, geophysics, high accuracy tests, and NGLR from the USA instead is just next generation lunar retroreflector. So up to now, this test I mentioned before performed through the arrays of retroreflector existing on the moon, so the 3 Apollo and the 2 lunokhod. And current opportunities for this next generation retroreflectors will be next year. In particular, our MoonLIGHT, as a MoonLIGHT will fly to the moon in 2024 with NASA CLIPS Prism-1A CP11 for short to the Rainer Gamma swirl. Instead, NGLR will go to another mission, CLIPS Ghost Blue, and always again next year. So this would be a kind of training. We can learn a lot from these opportunities, and in the future we can also learn and evolve this concept also to apply these next generation retroreflectors for detection of gravitational waves on the moon. In particular, so you see the retroreflector, we have the retroreflectors funded by National Science Committee number 2 of INFN. The Earth Pointing Actuator is funded by ESA, and we develop already, but we are not including in this this flight the robotic dust cover to protect the CCR from the dust deposition. So very briefly, this is the concept of the corner cube retroreflector, retroreflector, if you like, for short. CCR is very effective. It's essentially a prism made of out of a corner of fused silica, a cube corner of fused silica, and has a circular front face, and it employs a triple internal reflection, so that eventually what you get that incoming laser beam comes out from the same direction, the same direction of the incoming one. So in principle, you use obtain a far-field diffraction pattern from this retroreflector, and the angular size, it depends on the inverse of the front face diameter, and the intensity also depends on the front face diameter with a power of 4. So this is what we do, essentially the testing of the laser retroreflector for laser ranging missions is done in the SCF lab of Frascati. Essentially, it's an ISO 7 clean room with specialized optical support equipment, and I will not go into details, but you can read here the most important information is that from this lab goes out essentially payloads with technological readiness level larger than 7. In fact, you will see here a landscape, the Lunar big retroreflector, small array of retroreflectors for Mars and Perseverance. They are there on Mars already. A geodetic satellite were already launched on the 13th of July in 2022. So it's essentially another kind of LEGIOS. And here we have also application for Galileo second generation, so for GPS applications. And we have a joint lab with Matera, so effectively we provide the payloads, and effectively Matera laser range these payloads wherever they are, on the moon, on satellites, and so on. Not on Mars, unfortunately. So I introduce a little bit into detail the ISRO payload MPAC. You will see in the presentation, or MoonLIGHT or MPAC, they are equivalent. MoonLIGHT is just the big retroreflector, MPAC is the entire payload, which stands for MoonLIGHT Pointing Actuator. And this will go to the moon next year, in 2024, will be April, more or less the date. And I am the part of the project management office. I am also the science PI of this project. And here you see that is a modular payload. Essentially, there is a base frame or azimuthal frame where there is most of the electronic, the azimuth stepper motor. There is an elevation frame with an elevation motor, and there is a third passive block which contains the retroreflector and keeps isolated from the rest of the payload. Here's some generic information of the payload itself. And here some nice transparencies and views of the blocks of this payload. So there is also the possibility to integrate, to add a dust cover. At the moment, we discarded it from MPAC because of time constraints, also because of redundancy. So this is another possible risk if by chance doesn't open. So at the moment, we wanted to make it easy, and we didn't include. Also because you see the concept is different from the previous one. This is an old concept, but the structure itself is still that one. So moving next. So this is a brief summary of the history so far. Long story short, MPAC is one of the 2 science instruments selected by ESA. So we fly on board of Intuitive Machine 3 commercial mission within the Artemis program and the NASA initiative CP11, so Commercial Lunar Payload Service, Payload and Research Investigation on the Moon, or 1A. That was very long acronym, and now it's shortened in CP11. So I'll skip all this information. Be aware that besides MPAC, you have also other payloads like LUCEN, that is essentially an energy particle detector, CADR, which are autonomous rover with autonomous exploration capabilities, and Lunar Vertex, which essentially will measure the magnetic field of the landing site on the moon. So these are the milestones we passed. And this will be actually the landing site right near gamma squared. So it's a magnetic anomaly. That's why there is a magnetometer on board on this lunar vertex payload. Okay, I'll do this. Maybe it's better. And okay, let's move a little bit further. So this is just a generic landscape of the. It's not updated because it's from 2021, but makes a visual idea, a better idea what will be kind of the next CLIPS deliveries. And here in particular, you have the delivery site runner gamma, which where will be delivered MPAC. So why MPAC? Why a single big retroreflector with respect to the arrays nowadays on the moon? Nowadays on the moon, we have the Apollo arrays, the most effective ones. They are the most studied and the most laser-ranged one. They have two of them 100 retroreflectors. So, and one, the Apollo 15, has 300 retroreflectors. Each retroreflector has a diameter of 38 millimeter, while MPAC has is one retroreflector with 10 centimeter diameter. So why a single retroreflector? Effectively, because I demonstrate here that the laser return from a single retroreflector, such as MoonLIGHT, is the same as the laser return from the arrays. In fact, you have to take into account this, the following, that the moon moves with respect to the laser range station with a certain velocity aberration, so a relative difference in speed. So for the landing site, Reiner gamma, this is of the order, this velocity aberration is of the order of 4-7 microradians. So if you look at the response, let's say, of these retroreflectors, we are here, so between something like 10 million square meters, which is the optical cross-section for a single retroreflector of Apollo, and almost 200 for MoonLIGHT. If you take into account these numbers here, you take into account that Apollo arrays 11 and 14 have 100 of them, 15 has 300 of them. You take into account dust deposition, the current lunar arrays, so the reduction is 90% after almost 60 years. You take into account possible simulation for thermal effects, because thermal effects may degrade a little bit the response of the retroreflector. You take into account these numbers and you get this ratio. Namely, you can see by numbers that they are comparable. If you reduce if you take out actually the thermal effects, you get something that is quite close, again, to be comparable. So taking out the thermal effect means that if you measure, if you laser range this huge retroreflector when there is, for instance, night on the moon, thermal gradients there are not anymore, so the CCR is essentially isothermal. So in principle, you have these numbers here. So this is the first reason. The second reason is probably the most important one from a scientific point of view, because, you know, if you have arrays, the arrays have a size, typical size, and they are affected by the physical aberration of the moon. So in during the phases of the moon, you have at certain points that on the array, you have one corner cube, which is closer to the Earth with respect to the opposite corner of the array. So in principle, this introduces a temporal spread of the laser return. So if you fire a very short pulse, eventually what you get back is a larger pulse. This is of the order of nowadays roughly 1 centimeter. So this is the range accuracy you get because of this temporal spread. In 30 years, this reduced of a factor square root of the number of measurements. But you cannot go below because of this limitation, this physical size of the arrays. So here you have also another example. So this is the temporal spread introduced by the size of the arrays. And this should be the fiducial laser return if there's no libration. So MPAC will provide the opportunity to actually to exploit the full potential of the laser ranging station, because if you fire some laser pulses with this order here of 10, 20 picosecond, eventually you can get in a single shot the range accuracy down to below the centimeter level, a few millimeters for a single shot, not for many of them. And with many of them, you can go even down to 1 millimeter and below. So essentially, this is summarized in this table here. This is the current situation, what we can get from lunar laser ranging with the actual arrays. So these are limits on the accuracy we get on the weak and strong equivalence principles, beta parameter, variation, gravitational constant, geodesic precession, inverse square low deviation. So this would be what we could get with a pair of new retroreflectors like MoonLIGHT on the moon. And so we go down to the accuracy of 1 millimeter, and in a time scale of few years, at least 5, but I would say better 10, you will get something that range ultimate accuracy of 0.1 millimeter. And this is very important. And you can see here, I will not go into details. You can see here why lunar laser ranging technique is very important, and how, in principle, you can get estimates of the weak equivalence principle. Simply saying that if you violate this weak equivalence principle, you have a modulation of the range, Moon-Earth range, which depends with the periodicity of the synodic period of the moon. You compare it with the solution of JPL software, and eventually you get this number. But remember that, in principle, lunar laser ranging is sensitive to the composition of Moon and Earth. If you use also the data from the University of Washington with the torsion balance, in principle, you can take out this effect of the composition and get information constraints on the strong equivalence principle. And from this, you can get through the post-Newtonian parameters using the Cassini emissions measurements of the curvature parameter gamma. You can get a constraint on the beta parameter, which is one of the best constraints up to date. So we'll go faster here. You can get same constraints, similar constraints also for these other quantities, variation gravitational constant, also geodesic precession. You can also introduce limits for the, actually for the Yukawa-like, the strength of Yukawa-like potentials. And concerning the geophysical scientific objects, you can achieve this one from lunar geodesy, or if you prefer selenodesy, would be the right term to use. This next generation lunar CCR would be like fixed points on the surface of the moon. And so in principle, they can enhance our knowledge, our metric map, using also data from lunar reconnaissance orbit. In principle, you cannot laser range immediately MPAC with this, otherwise you will blow up the CCD. But if you have some small CCRs close to MoonLIGHT, in principle, this can work very well and can be also useful and can be part in such a fashion just described, can be employed as a part of the lunar geophysical network. Concerning the geophysical properties of the interior of the moon, lunar laser ranging is very sensitive to physical vibration, and physical vibration in turn depends on the moment of inertia of the mantle of the core, depends on tidal deformation, dissipation on the core mantle boundaries, and so on and so forth. So in principle, if we use MoonLIGHT, we can drastically reduce the issue of the vibration in the lunar laser ranging data. And they will not disappear completely, but we can greatly reduce them. And in principle, we can extract information. We can disentangle the vibration from the lunar laser ranging data, or reduce at minimum their influence. And so this can, in principle, allow to get more insights on the interior of the moon. So also this could be complementary to what Taichi Omura said before. Okay, this slide, I think I can skip because there were many persons, more experts than me. So I skip this slide, and I go directly to this concept: how we can employ next generation retroreflectors on the moon or gravitational waves detection. So in principle, I took this most of the content of this slide from our dear departed Stavros Katsanevas, so from this talk in 2021 at IGO. And currently, actually, what we can do in the future, okay, I told you that MoonLIGHT will be on the moon. This will be a training. We can test capabilities of our payload, and in principle, we can evolve the concept and use it for detection of gravitational wave. If we substitute, for instance, a mirror with MoonLIGHT here, MoonLIGHT is just Retroreflector, MPAC is the entire payload. We can do the link budget analysis. We can insert all the numbers here and calculate the shot noise, and considering an arm length of 3 kilometers, considering the fact all these quantities for reflectivity, transmission coefficients at the transmission and receiving telescopes, and all the information here. But here, even in the worst case scenario, it was considered the case in which retroreflectors are covered by dust, but eventually this will not be as soon as it will land on the moon. Even without cover, it will take years effectively to have a reduction, significant reduction in the laser return, but they are very close. And has an advantage that unlike a mirror, you can also not be so strict in the alignment, because laser retroreflector can reflect back, even though there is a small misalignment. So inserting all these quantities can get shot noise levels depending on the power of the laser, and you can get strain sensitivities here. So the idea would be to have two next generation retroreflectors, one on the lunar surface, and so perform operation for gravitational wave detection. One would be for lunar laser ranging purposes, and would be laser ranged by grass, Asimatera, and can also profit to the vicinity of a seismometer nearby, just to understand how it can be affected. And so, just to close here, the proposal is that for gravitational wave detector, MoonLIGHT can work maybe, I don't know if for LGWA, if you include a laser, in principle, yes, we will face some problems because this permanently shadowed region a problem also for MPAC, especially for the electronics of MPAC, for the pointing, automatic pointing. I don't know, but it can be used for sure for lunar seismic gravitational antenna. Can be also used for some concepts like LILA, or even the pathfinder of LILA. So this could be the application. And okay, these are the conclusions. I skipped them because essentially it's just a summary of what I said before. So thank you for the attention, the patience, and questions, please.
Questions?
Different kind of question. This is a very specialized field. So how you develop the community for that? Because the kind of the application for this lunar retroreflector, plus the kind of the calculations that are required actually to assess certain parameters. Even for example, the outer, the liquid nature of the outer core of the moon. So I mean, how you develop the community for this? This is my general question.
You mean for the, sorry, because I didn't hear very well because of noise. So you mean for the interior of the moon, how we can get information on this?
Yeah, so in general, in order to assess the data from this lunar retroreflector, the kind of the information that can be taken from these measurements, these are actually very specialized field. Within India, we don't have anyone. So I mean, I have a general query that how you develop the community for this kind of.
No, actually, okay, actually we don't do it in Frascati, INF and Frascati, because we just do the part of the payloads. But this is done for sure by a community of lunar laser ranging, and for sure also as part of the knowledge of laser ranging stations, because when they perform laser ranging operations and they get the data, they analyze and they have to take into account many models, not only the atmospheric model, but also other modeling to get back this data. And from this, what you get usually are raw data. There in the laser ranging station, they work on them and they get these constraints. So actually in INFN, we don't do it. We let this part of the job to Asimatera, which is part of the joint lab. So.
May I briefly respond to this question? Yeah. In passing, you must have seen this experiment called LARES. It's a lunar laser. It's not a. It's a laser ranging experiment, but not lunar. They have been working on this for 20 years. They just put retro-reflectors on a sphere, and they launch it in a low Earth orbit, and they laser range from ground stations in collaboration with the American laser ranging services to get the very accurate gravity model, the gravitational acceleration model. And they have used that for many years to determine the non-spheroidal nature of Earth, like the higher order modes of spherical distribution of the Earth, which then again folds back into satellite orbital calculations. It's all part of the celestial mechanics subject in Italy.
Okay.
Also continental drift and predict earthquakes. Yes.
Anyway, Sendil was also online.
Yeah. So the same network is also used to predict continental drifts and earthquakes also. If you have multiple stations, you can predict what is the torsion in each of the continental shelf and how much of deformation. So the geological aspect of this also.
There is also a question online.
Yeah, Marco, I had a couple of questions. The actuator that you have is to align it once towards the Earth, right? You have anti-azimuth alignment with 2 stepper motors on your cube corner.
Yeah.
This is one-time alignment. And you said that you use bigger cube corners compared to smaller ones because you wanted to minimize delay. I had 2 questions related to that. So for example, if you have this alignment, you can in principle, even an array, align it such a way that they all lie in the same plane. That's the first part. And the second question is that you still have the Earth's atmosphere. So if you start using picosecond, femtosecond lasers, what is the dispersion related pulse spread? Is that below 1 millimeter for a 7 kilometer atmosphere?
Okay, I replied. The first one is related to the actuation. Okay, I just speak a little bit about this actuation. Okay, we have azimuth and elevation. So in principle, what we perform is not continuous pointing to the Earth, because at certain point after the lunar day, we die. We don't have any more power. Sure. So our strategy is to point to the center of the vibration pattern so that we stay there forever. Sure. And so there are still vibrations. So in some cases, we would be just a little bit offset with respect to the center of the vibration. But in this case, we have the optimal pointing direction to the Earth. So I don't know if I replied correctly to the first question this way. Right. And for the second part of the question, yes, the fact that there is a divergence of the laser beam from the Earth to the Moon due to
not divergence. There is a phase delay error because of the atmosphere. You have dispersion. The shorter the pulse width you will use, the longer the dispersion and the longer the spread in your pulse width. See, one of the consequences of the tilted wavefront or tilted array you mentioned was the pulse is spread out because of the reflections from multiple reflectors. So if you use a picosecond light source, it's a broader bandwidth. You will have higher dispersion and the pulse would get broadened in the atmosphere twice while being launched and while being returned. Wouldn't that be comparable? Wouldn't that be comparable to millimeters for a 7 kilometer kind of a thickness of the atmosphere?
But this is already taken into account from the laser ranging station because they perform usually some operation with two colors laser ranging. So in this context, they have laser ranging.
Yeah, but that is fine for centimeters. Okay, that is fine for centimeters, but the moment you come to millimeters, I think you become comparable to the phase delay errors.
Yeah, I agree with you. In fact, they would proceed in parallel. I mean, because up to now you don't have the access to this kind of accuracy. So when there would be another effect that would be effect below at 1 millimeter or even below due to the atmosphere, this would proceed in parallel because we don't know yet what would be the effect there at 1 millimeter. So in principle, yes, you are right. I'm just overshooting in some sense because I'm saying that we can attain.
The last question is, you seem to use a solid cube corner for your system. And since it's a space launchable system, you would like to save on weight. So was a hollow cube corner ever considered? Since it's your laser is 1 micron, you can diamond turn aluminum 6061 or something like that and make a hollow cube corner with the same accuracy.
Sorry, I didn't get.
Yeah, you're using a solid fusilica cube corner.
Yeah.
The same cube corner can probably be realized by using a machined cube corner, which is hollow cube corner, where the three faces form part of a cube, but they're hollow. They're just aluminum surfaces which are diamond machined and coated with gold. The effective weight can be much, much lower for this large apertures compared to your glass. Was that considered, or why was it not a viable option?
So if I got right now, you're talking about hollow cubes.
Large aperture. Yeah, hollow cubes. For large apertures, you have a large weight saving on hollow cubes compared to solid glass, solid fusilica with similar accuracies.
So for the moment, as far as I know, for hollow cubes, there are problems in having big ones. Also because you have to, I don't know if someone is working now and has the answer that I don't have yet right now. But what I know up to now is that hollow cubes has problems. Actually, they can be deformed actually when they go to the vacuum. They cannot stay, the back faces cannot stay perfectly perpendicular. And if you introduce offset angles of these three back faces, eventually you spread your laser return over larger velocity aberrations. So what you get essentially is that though you have larger cubes, let's say, you get lower laser return because of this effect of the extra offset angles of the back faces. So it's not under control yet, as far as I know at the moment. But probably I'm wrong. Maybe there is a paper I'm not aware of. So
yeah, because with hollow cube corners, you just have three surfaces reflection. You don't have Fresnel loss from the front surface, volume absorption in the glass, and to add, the payloads are lighter. So you gain something. Anyway, I just was curious whether that was considered at all or not.
Yeah, this is just the concern of this possibility to reduce
stability and deformation.
Thank you. Thank you very much.
Thank you.
There's some, yeah.
Can they work with the multiple modes or there is a fixed wavelength it reflects? No, these laser rangers, are they specially designed for single mode or multiple modes light can be used? Yeah, multiple modes.
Multiple modes. Okay, actually
no, multiple frequency, different lasers.
Different lasers, yes. Yeah. For instance, they work. Okay, usually they work with a green laser, but they can work also very well with 1064 nanometers. So,
no, in the case of it is done through Earth, how do you, is there a mechanism to correct for the atmospheric changes?
To take into account these effects? This essentially is done in background by laser ranging station. They analyze they use two colors actually, so green and red, and they see what happens to the beam. There is a divergence, so after they model back. So this is specific to the laser ranging stations. They have these capabilities, this knowledge. Usually what they do they upload online is our raw data. Thank you.
Sorry, one of the attempts to address this problem was also adaptive optics. If you have a guide star, you could correct for the atmospheric aberration and launch a plane parallel beam from the top of the atmosphere by pre-correcting it.
No. Suresh, one is atmospheric correction, but I'm more worried about dispersion. If you're looking at time widths, the moment you go to picoseconds and femtoseconds, the dispersion, inline dispersion itself, because of the difference in refractive indices for different wavelengths.
Yeah.
Shorter the pulse you use, the larger the bandwidth, and that is what I think would become a limitation at some point. I don't know whether it will be 1 millimeter, but I think it becomes comparable at femtoseconds.
Got it. I got another question.
Let's postpone because I mean the speaker has to go. Okay, so let's move to the last speaker of the session. Thanks, Mark.
Thank you very much.